Hello everyone, I am Dr. Fawzul Atiq. I am giving some series of lecture on the course Probability and Statistics. And today we are going to discuss about the probability mass function for the case of a discrete random variable. So in this previous lecture, we have discussed about random variable, then its type, which are discrete type or continuous type. So today's talk is related to the discrete type random variable. Okay. So what is the probability mass function? So for a discrete random variable x, we define the probability mass function or PMF, probability mass function, PMF. PMF, it is a function from the real number set to a set 0, 1. I'll discuss why. So probability mass function, it is P of small p of some values, where the value which x can take. Right? So in the previous lecture, we have seen that x is a random variable, which is the sum of two dice in the experiment of rolling two dice. So x was taking some values, right? What are they? They are 2, 3, 4 up to 12. If you remember in the last previous lecture. So probability mass function is P of every real number you will take, but mostly these are the real number which are significant. Right? So it is the event that P of A is equal to P of the random variable whenever it takes this value, P of x equal to A. Right? So here A is for any real number, but now in our experiment, what is that small p of 2? It is the experiment that capital P probability of the event x is equal to 2, the random variable whenever it is taking this value. We have already seen this. This probability was 1 by 36, right? If you remember. So P of 2, this function gives this value. Similarly, P of 3 can be calculated. X is equal to 3. Now we said this is for any real number, right? So I am taking some value P of small p of 100. So this is basically probability of capital X is equal to 100. This value is definitely 0. You do not have such cases. So probability is 0, right? So probability mass function is a function which is depends on a random variable x, right? And sometimes that we denote this p function as fx of some value. Fx of a is equal to small p of a is equal to probability of x is equal to a, because it is depending on this random variable. So fx, right? So probability mass function is basically a function defined on from R to the real number to the set 0, 1. And why it is 0, 1? So it was taking some values. So you have a particular random variable x. First of all, that should be first thing. You have a random variable. So for this random variable, we define the probability mass function, that small p function, right? You can also sometimes say it is the fxx function, fx of x. It is a map from real number to the set 0, 1. Now why it is real number set? So this random variable have some value. Maybe it is this set where this random variable have some values. So suppose our that experiment, that rolling two dice, and x is the sum of the dice. So this portion was 2, 3, 4 up to 12. And these portions are the for any other real number other than these values. So this is the domain of this function p. So you have a function from here to here. So domain of this function is this, where you have some values here, which are the random variable takes this value, and these are other point of the real number set. And you have seen that p is P of any number which is belong to this domain, which is basically the real number, P of A, it is a probability, right? It is the probability of the event random variable value is x equal to A. So probability values are what? It can be either 0, 1, it will be within 0 and 1, right? And it can take any values between 0 and 1 because it's a probability. So this range set is actually the set 0, 1. So whenever P is taking from this function, it may have some positive values. It may have some positive values. It may have zero values also, but it may have some positive values. But if P takes some values, it is always 0, where the random variable do not take. So these values are always 0. So this probability mass function is a function from the real number set to the set 0, 1, to the closed interval 0, 1. And probability mass function is depends on a particular random variable of a particular experiment, right? So some properties we have already seen. This is a function from R to 0, 1. Now for a given B belong to R, if the random variable does not take the value B, that means, as we discussed, that B is a point somewhere here where random variable does not take. In that case, the probability is 0, P of x equal to 0. That's what it says. That then P of B equal to P of x equal to B, and it is equal to 0. Because this random variable will never take the value B. Next, another properties of the probability mass function. If x can take only the values x1, x2, x3, that means if the random variable takes some values x1, x2, x3, these values, then only probably that P of xi can be some positive quantity or 0. It can be 0 also, but it can give only in this place it can give the positive value. Other than that, P of x equal to 0 for all other cases, because our P function is from real number, right? Our P function is from the domain is the real number set. So whenever the random variable takes some values, only this real number P of that x values are some non-negative quantity. Otherwise, it is always 0, right? So this is again whatever we said. So that these values are giving some positive quantity. Other than that, for all these values, it is 0. It is this property. Now we have, since x must take one of the values xi, so we should have probability is I equal to 1 to infinity P of xi equal to 1. Why? Because we have already seen that whatever x values it was taking for this case of our rolling 2 dice example, it was taking 2, 3, 4 up to 12, right? But the P function is defined from R to the set 0, 1. So other than this point, this R has infinite number of points. But all of their cases, P of this value is of 0. And this is actually gives you the whole sample space. We have already discussed in the previous lecture. So if you take their sum, it is actually the probability of the whole sample space, right? And S is equal to union of x equal to 2, x equal to 3, and x equal to 12. Union x equal to b, where these b's are not here. So if you take their sum, it should give you the value 1. And therefore, sum of these values probabilities are also 1. Among these, some values have some positive quantities. Other than that, they are all 0, 0, 0, 0. Right? So x must take one of the values xi. Then we have I equal to 1 to infinity P of xi equal to 1. Next, the probability mass function is sometimes presented in a graphical format by plotting pxy on the y-axis and xi on the x-axis. How? Suppose look at this experiment. Consider the experiment of rolling pair of dice. The same experiment. Define the random variable x as the sum of the numbers appearing on the two dice. The possible values of x and their corresponding probabilities are given in the table. right? So whenever the sum is 12, sum is 3, we have already calculated the probability was 1 by 36. Whenever sum is 3, it is 2 by 36. Like that, whenever sum was 7, it is 6 by 36. Whenever the sum is 12, it is 1 by 36. All these probabilities are given, right? Then we can certainly plot them. We can certainly plot them in x-axis and y-axis. In x-axis, you will put the random variables. Suppose this is 1, 2, 1, 2, 3, 4, like that you may plot, right? It can goes up to 12. And in these cases, you will plot the probabilities, right? So we have already made it, so I can show you that. So this, whenever x is equal to 2, then p of x is this value, so you can plot it. 3, then it is 2 by 36. If whenever it is 7, it is 6 by 36. So in this way, you can plot them. And other than that, any this of this value, these values are 0. P of x equal to 1, it is 0, right? All values, it is 0. So you can plot the probability mass function. Next, look at this example. We'll try to find the probability mass function of this event. Just read the questions carefully. Read the situations carefully. 6 lots of components are ready to be shipped by a certain supplier. Number of defective components in each lot is as follows. Look at the table. So 6 lots are there, and each lot may have some defective piece, may not have. So in lot 1, you have 0 number of defective pieces of some particular component. Lot 2, you have 2 number of defective components. In the lot, maybe 200,000 number of components are there, but the defective piece is 2. In lot 3, there are no defective pieces. Lot 4, there are only 1 defective piece. Lot 5, there are 2, and lot 6, there is no defective pieces. In this way, it is given for the all 6 lots, how many defective pieces are there. Now, one of these lots is out of this 6 lot, one of the lot is randomly selected, right? One of the lot is randomly selected for shipment to a particular customer, right? And let X be the number of defective piece in that selected lot. So one lot is randomly selected out of 6 lot, and let X is the number of defective piece in that particular lot, selected lot. So X is a random variable. It is a discrete random variable. So it should have some probability mass function. So to find the probability mass function, first you understand that what are the values X can take. X is the number of defective piece. So X can take the values 0, 1 or 2, right? So because we have seen that number of defective pieces in these lots are, some cases it is 0, some cases it is 1, some cases it is 2. So X can take only these values 0, 1 or 2. Right? So the probability mass function we can easily calculate. Right? So probability mass function P of small 0, this particular thing is basically probability of capital X is equal to 0. Now what is the probability that the selected lot is having no defective piece? So out of 6 lot, these are the lot, the first, third and sixth lot. These 3 lots do not have any defective piece. So probability of X equal to 0 means then 3 divided by 6. It is 1 by 2. Is it clear? Similarly, that small p of 1 is what? It is probability of capital X is equal to 1. That means out of the selected lot, the number of defective piece is 1. So where it is possible, if you get this slot, number 4th one, so you have only one slot where you have only one lot where you have only one defective piece. So it is 1 by 6. Similarly, we have 2 is what? Probability of capital X is equal to. So if you only get this lot, the second or the fifth lot, then only you have 2 number of defective pairs. So the probability of this event is 2 divided by 6. It is again 1 by 3. Right? So in the probability mass function, we have already calculated where the random variable takes some values. Right? So this value is 0.5. This value is 0.167. So if you just round up, you can get this value, and 1 by 3 is 0.3333 like that. So what is the then probability mass function? Probability mass function is a function from real number to set to the set 0, 1 closed interval. So in this real number, if the values are 0, 1 and 2, it has some positive values, and other real numbers the values are 0. Right? So the probability mass function of this event is of this random variable x is p of x equal to this whenever x equal to 0 is equal to that, if x equal to 1 is equal to this whenever x equal to 2, and equal to 0 for all other real numbers. Right? So this distribution describes the probability of defectiveness in the randomly selected lot. So we calculated the probability mass function of this random variable x. I hope it is clear. Okay, now we have just one result which gives the other way, that we have already seen that if it is a probability mass function, then it should satisfy some properties. Now, which properties are sufficient to become a probability mass function? So look at the theorem. A function can serve as the probability mass function of a discrete random variable x if and only if values fx satisfy the following condition. You have two conditions. One is fx should be greater than or equal to 0, because you have seen that the probability mass function's range is 0 to 1. It is a probability. So the value should be either, it should be some non-negative quantity, right? And it should be within 0, within 1 also, but that part is covered in this property. So fx value should be always non-negative within its domain. And summation of all these values that where x can take, that means it is over the real number, but if it will, we have already seen that the values can take positive values within wherever x can take some values, right? So all of their sum should be 1, where the summation extend over all the values within its domain, and that value that sum should be 1. We have already seen in the previous example also, we have seen that if you just add them up, you should able to get that the values is 1. In other cases also we have seen the values are, if you take all of their sum, the values is 1. In these places it is anyway 0, so it is not contributing anything, right? So if you have the function satisfy these two condition, then you can say that function can be serve as a probability mass function of a random variable x, right? So then we can solve this example very easily. Check whether the functions given by fx equal to x plus 2 divided by 25, where x is equal to 1, 2, 3 up to 5. Can it serve as a probability mass function of a random variable for this function fx? Now look at the values. Fx equal to x plus 2 divided by 20. So f of 1 is what? It is 3 by 25. F of 2 is what? It is 4 by 25. Similarly, f of 3 is what? It is 5 by 25. F of 4 is what? It is 6 by 25. And what is f of 5? It is 7 by 25. So whatever values are given, we have calculated. Now all these values are non-negative. So the first condition is already satisfied. The next second condition is their sum should be equal to 1. Now if you just add them up, that f of 1 plus f of 2 plus f of 3 up to f of 5, if you just add them up, you'll get 3 plus 4, 7 plus 5, 12 plus 6, 18 plus 7, 25 divided by 25, it gives you 1. So the summation of that x over x, this value f of x equal to actually give you 1. So this sum is wherever the x values it can take. So it is taking the value 1, 2, 3 up to 5. So all of their sum is 1. So this function fx equal to this can serve as a probability mass function of a random variable, of a discrete type random variable. Right? So similarly, think about the next example. Now the next example says that gx equal to x minus 2 by 2. Now this one, if g of 1 is what? It is minus 1 by 2, right? So the first condition itself is not satisfying because it is a negative quantity minus 1 by 2 that is not satisfying the first condition itself. So you can say that no, this is not a is this gx is not a probability mass function of any random variable x which is of discrete type. Correct? So in this way, for any particular function is given, whether it can be a probability mass function or not, you can able to understand by the help of this theorem. Right? So we will discuss few more example, new concept in the next lecture. We have taken the content from these books, mostly from this book. Thank you very much. I hope you like the video. We'll meet in the next video. Thank you very much.